Hello, I'm Brooke. Welcome to Lab 4 Oscillations. So first, we're going to go over some concepts needed to understand the actual lab. We have Newton's second law. We've seen it all before. dP over dt, change in momentum over change in time, is equal to F net. And today, we have two forces creating our F net, our net force. We have the gravitational force and the spring force. And our net force is simply those added together. And then we also have to factor in a new concept, the energy principle, which is delta E is equal to work. However, when we set the system and the surroundings to be everything, work is zero because no outside force is doing work on the inside. So our delta E is equal to zero. And some energies that we'll be dealing with today include kinetic energy, which is 1/2 mass times velocity squared, potential energy, which is delta U for gravity and spring. For gravitational potential energy, it's mg times the height, or change in y position. And then the spring potential energy is found through an integral because the force is non-constant, and it comes out to be 1/2 ks squared. K it being the spring constant, and s being how compressed or extended the spring is. And then we also have some spring data given to us since the video we used today in the lab was pre-recorded. So we have the spring constant is 6.83, the mass is 0.402, and the relaxed length of the spring is 0.123. So goals of the experiment are to analyze the video of a mass at the end of a spring moving in a circular motion using tracker. Then we're going to construct a computational model using GlowScript. Finally, we're going to compare the results and answer some ending questions. So first, we observed the pre-recorded video by importing the video into Tracker, calibrating it, choosing the axis, and marking the position versus time coordinates. And there you see it moving around. So from this video and Tracker, we got the position coordinates, initial time, position, and velocity. We got the period, which is t. It's 1.524 seconds. With this period, you can calculate the spring constant, and with the spring constant, you can calculate the relaxed spring length, but we all already knew this. Moving on, we have the GlowScript model that we're using to compare the observed data. We have the mass, then the position, the velocity, initial. We have delta t, and we have time starting at 0. Then we have the gravitational constant, the spring constant, the relaxed length of the spring, and then we have L, which is the current length of the spring, L hat, the direction, and S, which is how compressed or extended the spring is. Then we have the different types of energy. We've already discussed this, kinetic, potential, and all the energy, the total energy is equal to all those added together. And then the calculation loop shows while t is less than 9.714 seconds, which is how long the tracker video lasted, we have the initial energies, we have force, the gravitational force, the spring force, the net force, velocity, and position update formulas, the spring force, and then finally the energy changes, which is just the current energy minus the initial. And then here is the product of this code. You can see, shows the spring oscillating. We have if we look at the bottom graph, we have the potential energy of gravity and spring opposite of each other. As it goes up, one goes up, the other goes down, and back and forth. And then we have the kinetic energy constantly oscillating as well. And the total energy is always equal to 0. This is because there's no work being done. Work is equal to 0. And then we look at the time y position and x position graphs, and we see the model is pretty close to the experimental. There are a couple reasons for this discrepancy. It could just be human error or outside forces acting that we aren't aware of, but it's very close. So what does this all mean? For the model system, is the energy principle satisfied? Yes, delta E is indeed equal to 0. The orange line would not be constant if the energy principle was not satisfied. And then we found two separate oscillation periods using the X and Y position data. We have X equaling 1.75 seconds and Y equaling 1.67 seconds. There's a little bit more discrepancy in the X period, however, the Y period should be used, and that's what we did, since the spring is operating in the Y hat direction. Thanks for watching.